So we spent a lot of time on this deep dive talking about the cloud as if it's this, I don't know, this magical ethereal dimension.
Yeah, absolutely. Like it just exists out in the ether.
Yeah, exactly. Just, you click a button on a web dashboard, and
Yeah.
somewhere out there, a server spins up, a database deploys, and your app goes live globally in like seconds.
And it's an incredibly compelling illusion. I mean, the tech industry has spent, the last 2 decades building that abstraction layer. And they did it specifically so you don't have to think about the concrete, right? The whole point of serverless computing or platform as a service is to completely decouple your software from the physical constraints of, copper wires and silicon wafers.
But the reality for you listening, if you really want to know how this works, is that there is no magic ether.
No, none at all.
The cloud is just someone else's computer. And if you actually want to understand how this infrastructure operates, whether you're an IT architect prepping for a massive deployment or, just insanely curious about the physical reality of the internet, you have to look at the concrete.
You really do. You have to look at how we take these cold, lifeless sheets of metal and turn them into that dynamic, intelligent abstraction layer we all use.
Which brings us to the core of what we're unpacking for you today. We're looking at a document that, honestly, I never thought I'd be this obsessed with.
It's a dense one.
It is. It's the official Supermicro SuperCloud Composer Bare Metal Installation Guide, specifically release 3.12.0 from June 2026.
Right, and on the surface, a 62-page technical installation manual for data center infrastructure sounds, incredibly dry.
So dry.
But when you actually read the workflow, it acts as a treasure map. It exposes the exact methodology of how a modern enterprise cloud environment is built from absolute scratch.
Okay, let's unpack this. Because before we get into the literal nuts and bolts, let's define what Super Cloud Composer, or SCC, actually is, right?
Yeah, that's a good starting point.
SCC is an infrastructure management platform. It's the orchestrator. So it is software that runs as a series of microservices on top of a Kubernetes cluster, specifically a distribution called RKE2.
Exactly.
And its entire job is to essentially look down at racks and racks of raw servers, network switches, storage arrays, and manage them.
Right, it's brain.
Yeah. And the manual notes, it handles these managed devices using protocols like BMC, Redfish, IPMI, and IKVM, which is a lot of alphabet soup.
It is, yeah. And we should probably clarify those acronyms right away because they literally form the physical nervous system of a data center.
3-2.
So BMC stands for Baseboard Management Controller. It is literally a tiny, completely separate computer embedded right on the motherboard of a server.
Wait, like a computer inside the computer?
Exactly. It has its own processor, its own memory, its own network connection, completely independent of the server's main, Intel or AMD CPUs.
So even if the main server is completely powered off or like the operating system is totally crashed, that BMC is still awake.
Yes. It's sitting there pinging the network, waiting for instructions.
That is wild.
And to talk to that BMC, industry standards were developed. So you mentioned IPMI, right? That's the Intelligent Platform Management Interface. That's kind of the older legacy protocol for doing this.
Okay.
Then there's Redfish, which is the modern RESTful API equivalent. It allows administrators to use standard web protocols to do things like query the temperature of a server's CPU or, force it to reboot.
So you can literally just send a web request to reboot a physical box.
Exactly. And then IKVM is interactive keyboard, video, and mouse. That basically redirects the physical video output of the server over the network so you can see the boot screen remotely, as if you're standing right in front of it in the data center.
Wow. Okay, so SCC uses all of these to manipulate the bare metal hardware from afar. It sounds like we are implanting a brain-like Kubernetes into the data center to control the body, which are all these managed devices.
That's a perfect way to look at it.
But to build that brain, you need a highly specific blueprint, which takes us to the first major section of this manual. It dictates that SCC must run on an RKE2 Kubernetes cluster.
Right. And Kubernetes, just for those who might not live in container orchestration every single day, is essentially a system for automating the deployment and scaling of containerized applications.
Right, instead of running a big monolithic app on one server.
Exactly. You break it into microservices, you put them in isolated containers, and Kubernetes shuffles them around your physical servers to balance the load and keep things running if, say, a piece of hardware dies.
But why RKE2 specifically? The manual is very rigid about this.
Yeah, that choice is highly deliberate by Supermicro. RKE2 is the Rancher Kubernetes Engine 2. It's known in the industry as the government-grade distribution.
Government grade, like for the military.
Basically, yeah. It defaults to incredibly strict security profiles, uses FIPS-validated cryptographic modules, and it strips out a lot of the legacy, less secure components you'd find in just vanilla Kubernetes.
I see.
When you're building a control plane that has root access to power cycle every server in a multi-million-dollar data center, you just don't use a lightweight hobbyist orchestration engine.
That makes a lot of sense. Now, the architecture also demands a component called Harbor. The manual specifies this must be deployed as a local container registry.
Yes, Harbor is critical.
Because usually when you deploy an app in Kubernetes, it reaches out to the internet, right? To Docker Hub or some public cloud registry to download the code.
Normally, yes. But Harbor brings that entire repository in-house. It stores the SCC container images and Helm charts locally on the cluster's own storage.
So it's basically hoarding all the files locally.
Right. And this is a non-negotiable requirement for enterprise security. You cannot have the core management engine of your entire data center reliant on a public internet connection just to pull a critical software patch. Oh, because if the internet goes down.
Exactly. If an upstream DNS provider goes down or, an underwater fiber cable gets cut, your data center management would be totally paralyzed. Harbor localizes the entire software supply chain.
Okay, so we have this secure localized brain, but the manual dictates a very strict rule for the control plane, the master nodes that run the cluster.
The node counts, yes.
Right. You can have exactly one master node, or you can have 3 master nodes. You actually cannot have 2.
Yeah.
And this just seems so counterintuitive to me. Like, if you are building for reliability and hardware is insanely expensive, wouldn't 2 nodes be a logical middle ground? If one dies, you have a backup. Why is 2 forbidden?
It seems logical until you dig into the actual mechanics of distributed consensus algorithms.
Okay, break that down for me.
So the brain of a Kubernetes cluster is a highly available key value store called etc. It holds the absolute truth of the cluster, which containers are running, what the network routing looks like, what IP addresses are assigned to what.
It's the master record. Right. And for etc. to commit a new piece of information to its database, the master nodes must agree on it. They have to vote.
They need a mathematical majority, like a quorum.
Precisely. If you have one node, it has 100% of the voting power. It decides reality.
Simple enough.
But if you have 3 nodes, you need 2 nodes to agree to form a majority. So if one node catches fire, the remaining 2 still constitute a quorum, and the cluster just continues operating seamlessly.
But if you introduce a 2-node configuration, the math falls apart.
Right.
Let's say you have node A and node B, and a network switch between them just goes offline.
This is the classic split brain scenario.
Right. Node A is completely healthy, node B is completely healthy, but they can't talk.
Right. So node A looks around, sees node B is gone, and tries to take control. Node B looks around, sees node A is gone, and also tries to take control.
But neither can get a majority.
Exactly, because one vote out of a 2-node cluster is exactly 50%, and a majority requires over 50%. Because neither can establish quorum, etc., just freezes to protect the data. It intentionally halts the entire cluster to prevent node A and node B from making conflicting changes that would permanently corrupt the database.
So by adding a second node, you actually doubled your points of failure.
You did. If either node goes down, or the network between them even just stutters, the whole system freezes. You have to have 3 to provide a tiebreaker. The mathematics of distributed reliability actively dictate your physical hardware purchasing decisions.
That is wild. You can't cheat the math. And speaking of physical hardware, that investment is not trivial at all. When we move from the architectural concept to the actual foundation, the hardware prep section of the manual, the requirements are staggering.
They really are. It's a heavy lift.
Let's start with the operating system layer. The manual provides a supported list. You can use Ubuntu 22.04 or 24.04, Red Hat Enterprise Linux 9.4, 9.5, or 9.6, and Rocky Linux or Alma Linux 9.5.
Standard enterprise distributions.
Right. But the critical constraint here is uniformity. The OS distribution and the exact minor version must be identical across every single node in the cluster. You can't run the master nodes on Red Hat 9.6 and the worker nodes on Ubuntu 24.04.
No, absolutely not.
But why is SCC so dogmatic about this. I thought a container was supposed to be OS agnostic. Isn't that the whole pitch of Docker and Kubernetes? Runs anywhere?
Well, the application inside the container is agnostic, sure, but the Kubernetes engine itself is deeply intertwined with the host operating system's kernel.
Okay, how so?
Kubernetes relies heavily on kernel features, things like SLE groups for resource allocation, and highly specific networking modules like eBPF or IPTables just to route traffic between the containers.
Right.
Different Linux distributions use slightly different kernel versions. They have different networking stacks, different system libraries like glib.
So if a master node schedules a complex networking container on a worker node,
And that worker node has a slightly older kernel module because it's running, say, an older version of Rocky Linux, the network route simply fails. When you are building a bare metal cloud, you are essentially fusing multiple independent servers into a single cohesive mainframe. Any variation in the underlying kernel behavior introduces microscopic inconsistencies.
and at scale, that's a disaster.
Exactly. At the scale of tens of thousands of network requests per second, those inconsistencies turn into catastrophic, totally untrackable bugs. Uniformity is the only way to guarantee stability.
And the compute power required to maintain that stability is immense. The manual outlines the CPU and RAM minimums. For a single master node running local storage, you must provision 24 CPU cores and 80 gigabytes of RAM.
It's massive.
If you were doing a 3-node setup, it's a minimum of 20 cores and 64 gigabytes of RAM per node. And this is exclusively for the management plane. This isn't running user applications. This is just the overhead software required to manage the data center.
It sounds absurdly high for management software, I know, but consider what those cores are actually doing all day. A modern Kubernetes cluster is incredibly loud. Well, you have the API server processing thousands of internal requests, etc., is constantly encrypting and writing state changes to disk. The kubelet agent is monitoring container health every few seconds.
Okay, yeah, that's a lot of traffic.
Plus, Prometheus is scraping telemetry data from every single piece of hardware in the rack.
Right, and the manual actually includes a specific warning note regarding large-scale AI deployments here.
Oh, yes.
It states that if you are managing infrastructure with heavy GPU, power, and cooling density, these baseline requirements might not even be enough.
Because the telemetry generated by hundreds of high-wattage AI accelerators will saturate those 24 cores just trying to process the heat and power metrics.
Just reading the thermometers maxes out 24 cores.
Literally, yes. You are monitoring thousands of thermal sensors in real time. If a liquid cooling pump fails in an AI rack, the orchestration engine needs to know instantly so it can migrate workloads or shut down GPUs before they physically melt.
Wow.
That level of real-time polling requires serious, dedicated compute overhead.
Okay, so we have the CPU and RAM. We also need to examine the drive layout required for these nodes because it is remarkably rigid.
Very strict.
The OS drive must be a 512 GB SSD. If you choose to manually partition it rather than letting the installer do it, the manual gives strict instructions. At least 256 GB for the var directory, 32 GB for opt, and 32 GB for root.
Right.
And the emphasis on var taking up half the drive isn't an accident, is it?
No, it's a foundational requirement of container runtimes like container. When Harbor pulls down a container image, or when Kubernetes extracts an image to actually run it, all of those cryptographic layers and file systems are stored in varlib containered or similar directories.
So what happens if it fills up?
If the var partition hits 100% capacity, the container runtime can no longer write temporary files or extract new images. The node will immediately go into a disk pressure state.
Disk pressure.
Yeah, and then Kubernetes will frantically try to evict workloads to free up space, and if it can't, the node effectively just dies.
That sounds stressful.
It is.
And the opt directory getting 32 GB is also interesting. That's usually where third-party software goes in Linux. In this context, it's where SCC stores the container network interface binaries and offline registry assets during the initial bootstrap phase.
Exactly.
But the OS drive is just the beginning. The manual requires a secondary drive, specifically for a storage system called Rook-Ceph. This must be an SSD between 512 GB and 1 TB. And the text issues a very stark warning. This disk must be wiped completely clean.
Yes, absolutely no file system.
No partition table, no lingering metadata, nothing.
This is a critical point of failure for bare metal deployments. If you take a drive that was previously used in, say, a Windows server or an old RAID array, it will have a GUID partition table, or GPT, or a master boot record written to the very first sectors of the disk.
Even if you deleted all the files.
Even if you deleted the files. The Kubernetes storage provisioner looks at the raw block device, and if it sees even a microscopic trace of an old partition table, it assumes the disk is currently in use and refuses to touch it, just to prevent accidental data loss.
Makes sense. Now, the manual also mandates that the device paths for this secondary drive must be identical across all nodes.
This is where it gets tricky.
Right, so if the operating system recognizes the drive as devvn1n1 on the first server, it must be exactly devvn1n1 on servers 2 and 3.
Right.
And we should probably quickly define NVMe for context. Non-volatile memory express is a storage protocol specifically designed for high-speed flash drives. Instead of going through older, slower controllers like SATA, an NVMe drive plugs directly into the PCIe lanes of the motherboard, communicating almost directly with the CPU.
Which is incredibly fast, but it's exactly why the device naming can get so complicated. Depending on which physical PCIe slot the drive is literally plugged into, the Linux kernel might name it NVMe1n1 on one server and NVMe1n1 on another.
Just because of the physical slot.
Yes. And the automated installation script is hard-coded to look for a specific string. If you tell the installer to use NVM1n1 and node 2 has the drive mapped as NVM0n1, the script just fails.
So how do you fix that? Do you have to open the server and move the drive?
You could, but to solve this in software, the manual instructs administrators to use Logical Volume Manager, or LVM.
Okay, LVM.
Right. If your hardware paths don't match, you use LVM to create a virtual abstraction layer. You pull the physical drive into a volume group, and you carve out a logical volume with a standardized name like dev storage data across all nodes.
So you are basically using software to force hardware consistency.
It's a recurring theme in bare metal provisioning. Software automation expects absolute uniformity. When the physical world fails to provide that uniformity, you have to build intermediate software layers just to trick the automation into working.
Here's where it gets really interesting, though. There is a requirement for a tertiary drive. A third, dedicated 512 gigs of NAB SSD. The manual calls this the SCC artifacts drive.
Yes.
And I have to push back here.
Yeah.
Dedicating an entire half-terabyte high-speed NVMe drive just for artifacts seems, well, excessive. Isn't that just a fancy download folder?
Yeah.
What exactly qualifies as an artifact in this context to justify that kind of dedicated hardware?
I get why it sounds like overkill. But in a supercloud environment, artifacts are the massive payload files required to manage thousands of distinct physical machines.
Like what kind of files?
We are talking about baseboard management controller, firmware updates, BIOS update packages, heavy Linux and Windows ISO deployment images, and customized, pre-configured golden images for spinning up new tenant servers.
Oh, golden images are huge.
Exactly. A single golden image for a data science workload with all the PyTorch and CDA libraries pre-installed could easily be 50 to 80 gigabytes.
Oh, wow. So if you dump a few of those onto the primary OS drive,
you immediately saturate that var partition we talked about earlier.
And the cluster dies.
Precisely. If a junior administrator uploads 3 massive golden images and accidentally fills the OS drive, they don't just fail to upload the 4th image, they crash the entire Kubernetes cluster because etc. can no longer write its state changes to disk.
That is a massive blast radius for a simple mistake.
Which is why, by physically separating the artifact storage onto a tertiary NVM drive, Supermicro is enforcing a hardware-level firewall for storage capacity.
Ah, I see.
The user-uploaded content is physically isolated from the critical operating system and orchestration data. You can completely fill the artifact drive, and the brain of the cluster will just continue ticking without issue.
Okay, that makes perfect sense now.
Yeah.
So we have these beefy, heavily provisioned, meticulously partitioned 24-core servers racked and powered, but right now they're just isolated islands. To turn them into a cluster, we have to wire them together.
The nervous system.
Exactly. This brings us to the networking and synchronization mandates of the manual. First up is IP addressing. The manual strictly outlaws DHCP, the Dynamic Host Configuration Protocol for the cluster nodes.
Yeah, DHCP is a nightmare for infrastructure.
Because DHCP is the protocol your home router uses to hand out IP addresses to your phone or laptop. It's convenient, but those addresses are leased for a specific amount of time.
Right, they expire. And if a lease expires while a server is rebooting, a DHCP server might assign it to a completely different IP address when it comes back online.
And if a master node's IP address changes unexpectedly.
The internal routing of the Kubernetes cluster is destroyed. The worker nodes wouldn't know where the API server went, and the other master nodes would think a member of their quorum had permanently died.
Static IP addresses are absolutely mandatory.
Yes.
The manual is also equally strict about host names. They must be lowercase, alphanumeric, and can contain dashes, but absolutely no dots. And you are explicitly forbidden from naming a machine localhost.
The prohibition on dots is tied directly to how Kubernetes handles internal DNS, or domain name system routing.
How does that work?
Kubernetes uses a system called core DNS to resolve internal microservice names to their temporary IP addresses. If you put a dot in a host name, the internal DNS resolver can misinterpret it as a fully qualified domain name.
Oh, like a website address.
Exactly. It might try to route traffic out to the public internet to resolve a name that only actually exists inside the cluster.
And naming a machine localhost is basically a self-inflicted network black hole, isn't it?
It's hilarious, but yeah.
Because localhost is universally understood by networking stacks as a loopback address 127.0.1. It means this specific machine. If Kubernetes tries to send a packet to a node named localhost, the sending node will just route the packet back into its own internal network interface.
The traffic literally never hits the physical network cable. It just loops endlessly.
That's a great way to break a deployment. Now, to facilitate the actual installation across the network, the manual requires the setup of passwordless SSH keys. Secure Shell is the standard protocol for remotely accessing Linux servers.
Right.
But the Python installation script can't just pause on node 1 and ask you to manually type in the root password for node 2 midway through a massive deployment. It needs automated access.
It has to be passwordless.
So the manual specifies generating an SSH key, pair a public key and a private key, using the ED25519 cryptographic algorithm. You keep the private key on the primary node, and you manually copy the public key into the authorized keys file on every other node in the cluster.
Yeah.
And you can do this as the root user or as a privileged user with passwordless pseudo-rights. ED25519 is notable here because it's a modern elliptic curve cryptography standard. It provides stronger security and significantly faster performance than the older RSA keys.
And that speed is critical when a script is opening hundreds of SSH connections in a matter of minutes to push configurations.
Now, I do want to push back on the premise of this manual for a moment, though.
Okay, let's hear it.
We are looking at an enterprise deployment guide from 2026. Why are we relying on a bespoke Python script executing SSH commands in a loop? I mean, the industry standard for infrastructure deployment is using declarative tools like Terraform or Ansible. You write a configuration file stating, I want 3 nodes configured like this, and the tool figures out the steps. Why are we manually generating SSH keys and running a sequential Python script like it's 2012?
It's a very valid critique, and it highlights what we call the bootstrap paradox of bare metal computing.
The bootstrap paradox.
Yeah. Terraform and Ansible are fantastic tools, but they generally require an existing stable environment to run from, and they often rely on a state file stored in a cloud bucket somewhere.
Oh, right.
When you are standing in a cold, dark data center staring at racks of blank silicon, you are at day 0. You are building the platform that will eventually run Terraform.
So you have to pull yourself up by your own bootstraps.
Exactly. You need the absolute lowest common denominator to establish the initial beachhead. Python is universally installed on almost every Linux distribution by default. SSH is universally installed.
So it's just about minimizing dependencies.
Right. By relying on a Python script over SSH, Supermicro ensures the installer can run on bare bones, freshly installed operating systems without requiring the customer to first build a complex deployment pipeline just to install the deployment pipeline software.
Okay, that makes sense. You sacrifice elegance for absolute reliability.
It is archaic, but it is deeply pragmatic for day 0 operations.
But out of all the requirements in this networking section, the one that requires the deepest dive is the absolute obsession with time.
Oh, the NTP requirement.
Yes. The manual dedicates a highly granular section to Network Time Protocol, or NTP. Every single node in the cluster must synchronize its clock to the exact same NTP source over UDP port 123.
It's vital.
If you're using Ubuntu, you configure the systemd time synced daemon. If you're using Red Hat, you configure the Crony daemon.
Right.
And if this is an air-gapped system, meaning a highly secure environment with no physical connection to the outside internet, the manual demands that you provide an internal Stratum 1 or Stratum 2 NTP server.
Which is serious hardware.
Yeah, a Stratum 1 server is a machine directly connected to a highly accurate hardware time source, like a GPS receiver or a localized atomic clock. You literally have to bring a piece of satellite hardware or a cesium block into the data center to keep time.
You do.
The manual even explicitly notes that in an air-gapped Ubuntu setup, you must open the configuration file and leave the fallback NTP setting blank, ensuring the server doesn't desperately try to ping public internet time servers when it realizes it's offline.
Right, because it would just hang.
But why? Why does a fraction of a second matter so much to a cluster of servers? We aren't calculating orbital mechanics here. We are managing infrastructure. It's not a Swiss train station.
What's fascinating here is that in distributed computing, time is the only objective reality these machines share.
Okay.
Think about the basic act of troubleshooting an error. If a database container on node A crashes and a web server container on node B throws a connection error, an administrator needs to look at the logs to figure out what happened.
Right. You need to know if the database crashed first, causing the web server to fail, or if the web server sent a corrupted request that caused the database to crash.
Exactly. You establish causality based on timestamps.
Okay, fella.
If node A's clock drifts ahead by just 50 milliseconds compared to node B, the logs will show the web server error happening before the database crash.
Oh, so causality is inverted.
Yes. The administrator will spend days chasing a ghost, trying to figure out how the web server broke the database when the reality was the exact opposite. Perfectly synchronized time is a prerequisite for system observability.
That explains the operational headache, sure. But there is a structural reason as well, isn't there? It ties back to security and consensus.
Absolutely. The entire Kubernetes control plane relies on mutually authenticated TLS transport layer security.
Like when you go to a secure website.
Exactly. Every time an API request is made internally, the nodes present cryptographic certificates to prove their identity. Certificates have strict expiration windows down to the exact second.
So if the time is off,
If node A's clock drifts 5 seconds into the future, and node B presents a freshly generated certificate, node A will evaluate the timestamp, conclude that the certificate was supposedly generated in the future, and instantly reject it as a potential replay attack or forgery.
the security handshake fails. And if the security handshakes fail, the etc. nodes can no longer communicate.
Which means quorum is lost. The database freezes. The entire multi-million-dollar cloud infrastructure comes to a grinding halt entirely because one server thought it was 2.05.01 p.m. and another thought it was 2.05.06 p.m.
Wow.
In a decentralized architecture, time isn't just a metric. It is the cryptographic glue holding the cluster together. They must tick in atomic unison, or the shared reality shatters.
That is just incredible. Okay, so our hardware is meticulously partitioned, our network is statically routed, our SSH keys are distributed, and our atomic clocks are synchronized to the millisecond.
We're ready.
The infrastructure is prepped. We now have to make a major architectural decision regarding storage. During the setup script, the manual forces you to select a Kubernetes storage class. This is how the cluster will store all of the persistent data generated by the SCC microservices.
Right, the vault.
You're given 3 distinct options: local Ceph file system using Rook-Ceph, an external Ceph CSI cluster, or an external NFS client. Let's break down the mechanics of these options.
So Rook-Ceph is what we call hyper-converged infrastructure. Ceph is an open-source, highly scalable distributed storage system. Rook is a storage orchestrator for Kubernetes that essentially installs and manages Ceph inside your Kubernetes cluster.
Inside the cluster. Okay.
If you choose this option, Rook-Ceph takes those dedicated secondary 512 gigabit SSDs we installed on each node and pools them together over the network into a single, massive virtual storage array.
So the advantage here is total self-containment. You don't need to purchase or manage a separate storage area network hardware appliance.
Right, it's all in the box.
But the disadvantage is compute overhead. Running the complex algorithms required to manage distributed storage requires a significant amount of CPU cycles and memory.
That is exactly why the hardware requirements for the master nodes jump from 20 cores up to 24 cores if you select local Rook-Ceph. The storage engine is actively competing with the orchestration engine for physical resources.
How does Ceph actually store the data across the nodes?
Ceph uses an algorithm called CRUH controlled replication under scalable hashing.
Catchy name.
It really is. When an SCC database writes a piece of data, the CRUH algorithm calculates exactly how to chunk that data and where to place 3 separate replicas of those chunks across the different physical nodes.
So if a power supply explodes and instantly kills node 2, the data isn't gone.
Exactly. The cluster recognizes node 2 is dead. The CRUSH algorithm queries the surviving nodes, finds the remaining replicas of the data, and instantly begins rebuilding the lost chunks onto the surviving drives to restore the redundancy.
It provides enterprise-grade data resilience using cheap, commodity solid-state drives right inside the servers.
Yeah, it's brilliant.
But you have alternative options. External Ceph CSI or an external NFS client. The manual notes that for external Ceph, you have to input a massive block of configuration parameters. The cluster FSID, monitor IP addresses, authentication credentials, specific volume names.
Just a lot of configuration.
And CSI stands for Container Storage Interface, right?
Yeah.
In this mode, Kubernetes isn't running Ceph, it's just reaching out over the network to a massive dedicated Ceph cluster managed by a completely separate storage team.
Exactly.
For the external NFS client, it's much simpler. Network file system is an ancient, incredibly reliable protocol for sharing files over a network. You simply punch in the IP address of the NFS server and the exact directory path it is exporting.
Choosing between these is fundamentally about architectural delegation.
How do you mean?
Well, using local Rook-Ceph is kind of like building a highly secure, heavy steel vault directly in the basement of your house. It is fully under your control, it doesn't rely on external roads, but it takes up a massive amount of space and structural support, in this case CPU and RAM. Choosing an external NFS server or an external Ceph cluster is like using a centralized bank down the street.
I see.
You free up all that space and compute power inside your own servers, allowing them to focus entirely on running the SCC microservices, but you introduce a heavy reliance on the network.
Because every time you need data.
Every time the application needs to read or write a piece of data, those packets have to leave the server, travel across the network switches, hit the external storage appliance, and come back. If the network team misconfigures a switch and introduces latency, your SCC databases will just grind to a halt waiting for disk I/O.
So the architect has to weigh self-containment and high CPU cost against network reliance and lower CPU cost.
Exactly.
Okay, assuming we've made that choice, the physical groundwork is complete, the foundation is set, we enter section 5, the build. It is finally time to actually push the button and execute the Python installer script.
The fun part.
The workflow splits based on your environment's internet access. If you are doing an online installation, the manual requires you to configure your firewalls to allow outbound traffic to a very specific whitelist of domains. This includes Ubuntu package archives, registry.k8s.io to pull the core Kubernetes binaries, Quay.io for third-party operators, and get.docker.com.
Pretty standard for an online K8s build.
Right. But if you are operating in an air-capped environment like a defense contractor or a highly secure financial institution, opening firewalls simply isn't an option.
No, they would never allow it.
So instead, you have to manually transfer 2 files onto the primary master node. First, a relatively small .tar.gz archive containing the installer.py script and some basic configuration files.
Yep.
Second, a massive offline bundle file, also ending in .tar.gz, which contains gigabytes of prepackaged container images and binaries. And the manual issues a critical warning here.
Oh, this is important.
You extract the first file, but you absolutely do not extract or rename the massive offline bundle. You simply move it into the extracted installer directory.
The Python script is designed to handle the extraction of that massive bundle dynamically during the installation process.
So don't try to be helpful.
Exactly. If an administrator tries to be helpful and unzips it beforehand, the script won't find the specific .tar.gz file signature it expects, and the entire installation fails before it even begins.
Good to know. So when you execute installer.py, it drops you into a terminal menu detailing 4 distinct stages that must be executed in exact sequential order.
Yeah.
Let's walk through the mechanics of what this script is actually doing to the bare metal.
Sure.
Stage 1 is setup host. When you hit enter, the script uses SSH to connect to all the nodes. It verifies host names, checks that the OS versions match, and configures required Linux kernel modules like Burnet filter for network bridging.
It's laying the groundwork.
Then it initiates the actual installation of the RKE2 Kubernetes engine, bootstrapping, etc., and forming that critical cluster quorum we talked about.
Right. And then stage 2 is install upgrade infracharts.
What happens here?
This is where the script begins deploying foundational third-party software on top of the fresh Kubernetes cluster. It deploys the Harbor local registry, PostgreSQL for relational database storage, Redis for high-speed caching, and Prometheus for telemetry.
And the manual specifies these are deployed using Helm charts. We should clarify what Helm is. If Kubernetes is the operating system, Helm is basically the package manager, right?
That's a great analogy.
Instead of manually writing thousands of lines of YAML configuration to deploy a complex database cluster, A Helm chart bundles all those configurations, services, and network routes into a single package with variable templates.
Yes. The Python script essentially feeds a values.yaml file to the Helm engine, and Helm deploys the entire database architecture with a single command. It's a massive force multiplier for automation.
Okay, so that's stage 2. Stage 3 is push SCC charts and images.
This is a heavy stage.
This is where the script takes all the proprietary SuperCloud Composer software, the actual application we're trying to install, unpacking it from the offline bundle, and pushing it into the local harbor registry we just built in stage 2.
Right.
And this brings us to one of the most revealing details in the entire manual. The text explicitly warns that during stage 3, the script might suddenly crash and throw a 500 internal server error on your terminal screen, with logs complaining about being unauthorized to access the repository.
Yeah, this is a classic race condition caused by resource exhaustion.
Explain that. Why does it crash?
Well, you have to remember, we just asked a brand new Kubernetes cluster to spin up a complex harbor registry database, and the moment it comes online, we immediately start hammering it with gigabytes of dense container image layer.
Oh, we were just flooding it.
Exactly. The disk I/O spikes, the CPU spikes, and the harbor database container essentially suffocates under the load and crashes. When the Python script tries to push the next image, harbor isn't there to answer, returning a 500 error.
What is remarkable is the official super micro remediation for this error.
It's so practical.
It is. The manual doesn't instruct you to rebuild the cluster or tweak complex kernel timeout settings. The official fix is essentially, wait a minute, and run stage 3 again.
It perfectly illustrates the self-healing pragmatism of Kubernetes.
How does it self-heal?
When the harbor database crashes, the Kubel agent detects that the container is no longer responding to health checks. Kubernetes automatically terminates the frozen container and spins up a fresh instance. By the time the administrator waits a minute and restarts the script, Harbor is back online, fully stabilized, and ready to receive the rest of the images.
Just give it a minute to catch its breath. I love that. Yeah. Finally, stage 4 is install upgrade SCC Helm charts. The infrastructure is built, the images are stored locally, and now Helm deploys the actual SuperCloud Composer microservices. Once the pods are running, the script asks you to create the initial admin password.
And you can't just use password 123.
Definitely not. The entropy rules are strict. It mandates a length of 6 to 12 characters, requiring at least one uppercase letter, one lowercase, and one number. Once submitted, the installation is complete.
The cluster is live.
So what does this all mean? It means we took raw, unconfigured metal, overlaid a synchronized Linux environment, bootstrapped a distributed consensus engine, deployed localized storage and registries, and finally launched the orchestration software. We can now point a web browser to the masternode's IP address on port 15588 and log in to manage physical hardware from a clean graphical interface.
It's a masterclass in stacking abstractions, it really is. But in enterprise IT, the initial deployment day 1 is a contained, predictable event.
Day 1 is easy.
Exactly. Day 2 is when reality collides with the infrastructure. Day 2 covers the operational realities of scaling, troubleshooting broken hardware, and managing upgrades.
Which transitions us to Section 6. Day 2 operations. And the manual dedicates extensive pages to troubleshooting, because when abstractions break down, they break down violently. Let's look at scaling first. If you deploy your SCC cluster and realize 6 months later that you need more compute power to handle hundreds of new managed devices, you need to add a worker node.
Right, you need to scale horizontally.
The process is generally straightforward. Prep the hardware to match the OS and network rules, boot the script, and select menu option 5 to join a node. But the manual outlines a severe limitation for air-gapped environments.
Yes, the serialization constraint.
In an offline setup, you can only add a worker node after the initial SCC Helm charts are fully installed and running. You cannot prep a massive 5-node cluster all at once during the day 1 script execution. The architecture forces you to establish the core brain first before you're allowed to graft on additional compute limbs.
It enforces a serialization of state. The cluster needs to be completely stable and running the SCC application before it can safely distribute the offline image bundles to new nodes joining the network.
Makes sense. We also need to revisit the Rook-Ceph local storage. We talked earlier about the strict requirement to wipe those secondary NVMe drives completely clean before installation.
Oh, yes.
The troubleshooting section details exactly what happens if you fail to do this, particularly during a reinstallation or hardware migration. The Rook-Ceph deployment will simply hang. The pods will sit in a pending or crash loop backoff state indefinitely.
And if you dive into the Kubernetes logs, perhaps using a terminal UI tool like K9s, you will find the storage provisioner complaining that it is skipping the NVMe device because it detected an existing file system contained Ceph Blue Store.
Even if you formatted the drive.
Yes, because Ceph doesn't just write a simple partition table, it writes deeply embedded metadata across the block device to manage its CRU-SH map and object storage. A standard operating system format command will not clue it.
Wow. So to fix this, the manual provides 3 brutal low-level Linux commands that must be executed directly on the raw block device. They read like digital demolition orders.
They really do.
First, you run secdisk zapall devman 1L1 1N1. What does that actually do?
So secdisk is a command line tool for manipulating partition tables. The zapall flag instructs it to aggressively destroy both the modern GUID partition table and the legacy master boot record on the drive. It strips the drive of its basic structural identity.
Okay, identity erased. Next, you run dd if dev0 of devanv m11 yum bs1 m count 100 a flag direct sync.
The dd utility is a bit stream copier. This command is telling the kernel to take pure zeros from the dev0 virtual device and write them directly over the first 100 megabytes of the physical flash drive.
Just blasting it with zeros.
Exactly. And the crucial flags here are direct and desync. They force the kernel to bypass all operating system memory caches and write the zeros immediately to the physical silicon, obliterating any lingering Ceph metadata at the start of the drive.
That sounds intense. Finally, the coup de grace, block discard devanv 1N1.
Right. Block discard is specific to solid-state media. It sends a low-level trim or UNME command directly to the NVMe hardware controller embedded on the drive itself.
Wait, to the drive's own controller?
Yes. It tells the hardware controller to instantly discard all internal mappings for every single flash block on the device. It forces the drive to completely forget it ever held data, returning it to a factory-fresh state. Only after executing this entire demolition sequence will the Rook-Ceph provisioner accept the drive and build the storage array.
It's a stark reminder that beneath the elegant Kubernetes YAML files, you are manipulating raw voltages on flash controllers.
It's very physical.
What about external storage troubleshooting? If you chose the external NFS client during setup, the manual notes a common failure where the installer halts during stage 2 with an error reading context deadline exceeded.
Ah, yeah.
This sounds like a network timeout, but what is the root mechanical cause?
It is a timeout, specifically in RPC or remote procedure call, timeout. When the Kubernetes NFS provisioner tries to connect to the external server, it requests a specific directory export.
Okay.
Let's say you told the installer script your NFS path is data storage. The provisioner reaches out to the NFS server and asks to mount that directory.
That sounds straightforward.
However, if the storage administrator configured the NFS server's /exports file to share ops storage instead, the server will silently reject the mount request because the path doesn't match its allowed list.
So it just ignores it.
Yes, and the Kubernetes provisioner just sits there, waiting for the connection to establish until its internal timer hits the deadline. It throws the context deadline exceeded error, and the entire deployment fails. A single misaligned character in a directory path between 2 completely separate servers breaks the automation chain.
That is infuriating, but perfectly logical. The manual also heavily details the realities of upgrading the platform. Software upgrades in the cloud era are often pitched as seamless, zero-downtime rolling updates, right?
Yeah, that's the marketing pitch.
But this bare metal manual outlines a very different reality. If you were running an older version, like SCC 3.1, and you want to upgrade to version 3.1, the architecture changed so fundamentally that an in-place upgrade is impossible.
No rolling updates there.
You have to perform a massive database backup, wipe the servers, deploy a completely fresh 3.11 installation, and carefully restore the configuration data.
This huge operation.
Conversely, if you are upgrading from 3.11 to the version we are examining today, 3.12, the software requires a hardware prerequisite.
The artifact drive.
Yes. Version 3.12 introduced the mandatory requirement for that tertiary 512 GB artifacts drive we analyzed earlier.
Right.
You cannot upgrade the software through a terminal command until a physical human being walks onto the data center floor, latches the server chassis, inserts a new physical NVMe drive, and reboots the machine.
The software evolution is entirely gated by physical hardware expansion.
But out of all the day 2 operations detailed in this 62-page document, the most treacherous is the procedure for changing an IP address on a master node.
Oh, without a doubt. It's the most dangerous operation in the book.
The manual dedicates nearly 5 full pages of dense terminal commands to this single task. In a standard operating system, changing an IP address takes 20 seconds in a network configuration menu. Here, it is treated as a highly dangerous operation that can permanently destroy the cluster. Let's break down exactly why this is so volatile.
It all routes back to etc. and the Raft consensus algorithm. As we discussed, etc. relies on strict, cryptographically verified identities to maintain quorum.
Right.
When a node joins the cluster, its cryptographic identity is permanently bound to its initial IP address.
Permanently, okay.
If a network administrator changes the IP address of a master node in the operating system, etc., doesn't dynamically update. To the surviving nodes in the cluster, the original nodes simply vanish without a trace.
And when it tries to reconnect?
When node tries to reconnect using its new IP address, the cluster views it as an unauthorized rogue server attempting a hostile takeover of the database. The security protocols actively reject the connection.
So you can't just change the IP and reboot. You have to perform a cryptographic eviction.
Yeah.
The process outlined in the manual is terrifying. You must log into a surviving healthy master node. You use a command line tool called attdel, but to even use this tool, you have to manually point it to the deeply buried cryptographic certificates, specifically the server-ca.crt and the server-client.key. So the tool is even authorized to speak to the database.
Once authenticated, you query the cluster to dump a list of all current members. The database returns a list of hexadecimal cryptographic ID strings. You must identify the exact ID string of the node whose IP address you want to change.
Okay, carefully select the right ID.
Right. You then issue a command to permanently remove that specific member ID from the cluster's consensus history.
I'm going to use an analogy here because reading this section of the manual feels exactly like reading a surgical textbook.
It really does.
This procedure is the equivalent of performing open-heart surgery on the cluster while the patient is awake and running traffic. You are reaching into the active voting memory of the database and amputating a piece of its consciousness. And the manual includes a severe warning box. If you copy and paste the round cryptographic ID string, you will amputate a healthy, functioning node.
And if you amputate a healthy node in a 3-node cluster, you immediately lose your quorum.
Oh no.
The remaining node freezes, the database locks up, and you have caused a catastrophic, potentially unrecoverable data center outage. The stakes for a simple copy-paste error are immense.
Once you successfully amputate the old identity, you log into the node with the new IP address. You update the local config.yaml file with the new address. But the node still remembers its old identity, right?
Yes, it has local files.
The manual instructs you to execute 2 destructive commands, rm-rf varlabrancher to servers and rm-rf barn and rm-rbrancher to servered betcity.
Those commands are physically deleting the node's cryptographic security badges and its local copy of the database state. You are wiping its memory completely clean.
So it's basically amnesiac now.
Exactly. Only after doing this can you restart the RKE2 service. The node wakes up, realizes it has no identity, generates fresh TLS certificates bound to the new IP address, and humbly begs the surviving cluster nodes to let it join as a brand new, empty member.
It is a stunning amount of operational friction for a simple network change. But it proves a fundamental point about modern infrastructure. If we connect this to the bigger picture, the cloud is not magical.
No, not at all.
No, it's not an ethereal space where things just happen effortlessly. It is incredibly literal.
The immense value of deeply analyzing a document like this super micro installation guide is that it aggressively grounds us in reality.
Yes, it does.
Whether you are building a server rack in your garage to learn Linux, whether you are walking into a technical interview for a senior DevOps role, or whether you just want to truly understand how the systems running our global economy actually function, you need this foundation.
Absolutely. We have explored the meticulous hardware preparation required just to get to the starting line, where perfectly matching OS kernels and 24-core processors are the absolute bare minimum entry fee.
Right.
We analyze the unforgiving reliance on hardware-based atomic time, where a clock drift of a few seconds will shatter cryptographic trust and bring a cluster to its knees. We weighed the architectural trade-offs of building a local storage vault versus relying on an external network bank.
And we walked through the abyss of bare metal troubleshooting.
Oh, the troubleshooting. From issuing hardware-level block discard commands to NVMe drives to performing cryptographic open-heart surgery on a live, etc. database, you now understand the anatomical structure of a supercloud. You know exactly what it takes mechanically and philosophically to build it from the concrete floor up.
It's a completely different perspective on how the internet runs.
It really is.
It is.
And as we wrap up this deep dive, I want to leave you with a evocative thought to mull over. We spend our entire days in the tech industry debating the merits of serverless computing and the cloud. We talk about these concepts as if we have evolved past physical machines, as if we have transcended hardware entirely.
We hear it every day.
But reading a manual like this reveals a profound, almost beautiful irony at the heart of computer science. The more virtual and abstract our software layer becomes, the more rigid, massive, and meticulously configured the physical bare metal underneath it must be.
That's the paradox.
You simply cannot have the infinite ethereal flexibility of the cloud without the absolute, unbending physical laws of 24-core processors, perfectly wiped solid-state drives, and atomic clocks ticking in absolute unison. The magic of the cloud is just someone else's beautifully orchestrated bare metal.
Very well said.
Keep digging into those technical manuals. Keep questioning how the abstractions work under the hood, and keep learning. Because once you understand the physical concrete, you will never look at the cloud the same way again.